Okay.
All right. Hi everyone. Welcome back. So today our speaker is Yijun. She's actually a postdoc right now in the Department of Computer Science at the University of Copenhagen. And she does like a lot of work there on fairness and fairness in machine learning. She got her PhD from the University of Science and Technology of China, where she was working in ensemble learning. And like her research interests in general have been on like the reliable and like trustworthy aspects of machine learning. And today she's going to tell us about her work on why we need new fairness metrics and how to use them. And that's all you.
Okay. Thanks. Thank you for having me here. And today I'm going to present my work in this field. And to be honest, this is all of my work in this field up to now. So I think I grew interested in this area because I think the AI and machine learning models is everywhere right now, and since they are trained on the data that are coming from the reality, and they may include discrimination issues and some real problem. So it will be meaningful to mitigate bias in these cases. But uh, to mitigate bias, a very important question would be how much amount of bias would that be? And based on this question become increasingly important because recent research shows that through human AI interactions, emotional and social biases could be amplified the most. Um, I mean, the researchers defined four scenarios in their experiments, like human AI interaction and human AI interaction, but human are told that they are interacting with humans. And also another scenario is a human and human interaction, but the human are told they are interacting with AI. And the last is a human and human interaction. And they find that the first picture, they find that the bias could be amplified the most in all of these four scenarios. So which means even small biases that exist in the machine models that could be leave human even more biased, and that could lead to a feedback loop. That is certainly not a good thing. So I summarized many fairness metric in the literature and find that most of them can only focus on only one aspect, which means they can only focus on either group fairness or the individual fairness. And we all know that meeting group fairness doesn't necessarily mean the individual fairness is met as well. And even within group fairness, since three non-discrimination criteria cannot be satisfied and are normally not satisfied at the same time, unless in trivial cases, which means even we can only consider group fairness, they cannot be satisfied all at the time, all at the same time. And despite that, the existing fairness measures, they are usually originally defined for one single and usually binary sensitive attributes. But in reality, we may face more complex cases. We may face more multi-value sensitive attributes, such as race, and we may also face more than one sensitive attributes. For example, in credit card applications, there may be involved race, gender, and age, and more than one set of attributes may exist. So in this case, which means the existing fairness metric may be limited in what we would actually use in practice. So I was thinking whether it is possible to consider both fairness, to consider both group fairness and individual fairness at the same time. And motivated by that, I proposed two fairness metric, and one is called the discriminatory risk. The idea is simple. I'm following the principle of individual fairness, that is, similar individuals should be treated or evaluated similarly, which means the treatment or evaluation on one instance shouldn't change solely due to minor changes in its sensitive attributes. So, so basically, here is how I do here. I would like to slightly change the sensitive attributes for one instance, and makes model predict it again. And if the model predicted differently, there will be certainly something biased here. But we cannot say for sure that there is no discriminant risk at all if the model predict exactly the same. So we can only detect if it shows some discrimination here. And this equation is evaluated on one instance, so it's supposed to evaluate, so it is supposed to consider from individual level aspect. And some may wonder how I perturb the sensitive attributes here. Basically, the idea is if the original instance coming from the privileged group, I will perturb it into any one of the unprivileged group, and if the instance coming from any one of the unprivileged group, it will be perturbed into the privileged group. So basically, the real problem is whether it doesn't really matter which marginalized group is this applicant coming from, but what really matters is it will be perceived into the marginalized group to see the model will predict differently. And if we calculate the discriminant risk over one data set or even a data distribution, so in this way, we were also considering the statistical perspective. So by putting them together, we were considering discriminant risk from both individual and group level aspects. And this equation is widely applicable because it allows more than one sensitive attribute, and each sensitive attribute allows binary or multiple values. And I should also mention that it is different from the existing fairness measures. Although it may sound like it may sound like a counterfactual fairness, but actually they are different. For example, counterfactual fairness is defined. Well, they need to be the models they're used in counterfactual fairness. They are usually causal models, but we don't have such restraints for the learning algorithm here that we are using. And in counterfactual fairness, they make the following changes for on the proxy attributes that may be affected by the sensitive attributes. They will also be taken into account. But in this case, we only consider the perturbs on the sensitive attributes only, which means we don't consider the following changes if sensitive attributes may affect some proxy attributes in reality. And I should also mention that it also has some limitations. For example, as I mentioned, since it can only detect if the equation equals 0, it doesn't necessarily mean the model is purely fair at all. Purely fair. So which means usually the value calculated using discriminant risk is normally smaller than using other group fairness measures such as demographic parity and equalized of opportunity. And except this one, I also have another fairness metric. It have a 3 version. It's called the harmonic fairness manifold. The idea is also basically if we view the instance as data point on certain manifold, then we expect the manifold representing the members from the marginalized group is supposed to be close as possible to that representing the member from the privileged group. So following this idea, we were trying to measure how much difference between those manifolds. And since we are using data set, we are actually this measure is built upon the Hausdorff distance, and that is used to evaluate the difference between two sets. And the sets by sets I mean the subsets representing the member from the privileged group or the unprivileged group. So the first version of it is called the previous HFM. It is for the one bi-valued sensitive attributes only, and so we directly use the Hausdorff distance let's say the equation 2, we are in this case, since this is a one binary sensitive attribute only, so the original data set will be partitioned into two subsets. And for example, if we just record the privileged group as the S1, the other one would be the S0 or S bar 1, whichever you like. And for each instance in S1, we will try to find the nearest data point in S bar 1. For then we will have several distance, and each distance corresponding to one element in S1. And so for the S1, we will get a maximal value, and we will do this exactly the same for S bar 1, and we will get a maximal value for the both for the two maximal values, and we will record it as the distance between S1 and S bar 1. And if we use the predictions in the equation, it will be recorded as df, representing the difference. So when the difference between marginalized group and the privileged group using the model. And if we are using the true label, that will be the difference between the marginalized group and the privileged group in the original data. And we will use equation 1 to calculate the previous HFM. And for the more than one sensitive attributes that could be possibly multi-valued, and we define the maximal or average HFM. They are defined in equation 3. And we will use a similar idea. Basically, if we consider one bi-valued sensitive attributes, for example, it have n values, and for each value, we will find the Sj and the S bar j to find the maximal value, and we will get n values, n maximum values, and we will get the maximal among all of them, and use that as the distance between set in this case. And if we use the average operator to replace the maximal operator here, we will get an average version of distance between set. And we will after we get a distance between set, we will use the equation 3 to get the maximum fairness measure in those cases. Since I should also mention that since calculating the Hofstadter distance is quite expensive, we also proposed the approximation algorithm to facilitate the calculation. I will lead in the later if we still have time. But given so many fairness metrics that we already have, we can still see that there is still some issues here. For example, if we are considering group fairness, and there is like one multi-valued sensitive attributes, and the easiest way to calculate them would be the binarization, which means we will treat the multi-valued sensitive attributes as a binary one. And in this case, we will find that the binary cases would underestimate discrimination. The 5A is the original definition of demographic parity. We can calculate equalized opportunity or predictive parity similarly. And the 5B is a binarization form of it. And I try to use the traversal-based generalization to handle the multi-value cases, which are 5C and 5D. If we use the average operator to replace the maximal operator here, we will get the average version of it. And we can see that the the maximum version of the traversal-based generalization would be much larger if we compare to the binarization form. And even for the average version, it is still larger than the original definition or the binarization version of it. And this tendency this pattern recurs across dataset regardless of the learning dataset in use. In these figures, I'm using different learning systems, but I only present one dataset here, but we actually observe similar observation across three datasets, and they are only one 5-value or 6-valued sensitive attributes. So basically, we can see that individual fairness measures are normally more stable in those cases. But if we use the traversal-based generalization, there would be another problem, which means their computation cost would be much higher than that. For example, if we can see from figure A and B, the traversal-based generalization of group fairness is they would cost nearly 9 times of that of the binarization version of the original definition. And if we consider individual fairness, the computation cost would be even higher. That could be twice or 4 times of that of the extension of the group fairness. So if we calculate the original binary version, that would be thousands of times of that, I guess. So it is clearly that if we are facing more than one set of attributes, degenerizing more than one set of attributes into one super discrete set of attributes would certainly not be an efficient way to handle this, because the computation cost would increase exponentially in those cases. Even we are just making like from binary cases to 5 or 6 cases, it still could be hard to take or hard to afford. And even if we use the approximation of the HFM and the multi-valued version would still cost more time. In this case, would be twice or 5 times compared to the binarized version. So basically, traversal-based generalization, they would just incur higher computation costs. And interestingly, we also find that individual fairness is somehow can signify the group fairness, which means when individual fairness is getting better, and it is also likely that the group fairness is also getting better. And if the individual, on the opposite, if individual fairness is getting worse, and it is also likely that group fairness is getting worse as well. And this is not only happening when we use the cell index. This is one of the individual fairness metric, and it also happens when we use the discriminant risk. This could be primarily viewed as one of the individual fairness, although it can also consider group level aspect as well. So we were thinking, given all of this fairness metric, what can we do to mitigate bias in these cases? And whether it is possible to increase both group level and individual level of fairness aspect. So we were thinking maybe, so we were proposing a fairness metric. It is called FairShot. This is a pre-processing framework. It could work for tabular data, and it could also use different Shapley value calculation. The idea is we are trying to modify one data set and train the model on the adjusted data set, and hopefully retrained model would be fair than compared to the original model that is trained on the original data set. Then how would we modify the data set? So firstly, we would partition the original data set into two parts based on the sensitive attributes, and then we will calculate Shapley value using BR as a value function. In this case, we were trying to figure out which feature would be more important in making bias decision. And if we find those features, we will try to modify those features. And we will use the closest neighbor. Let's take the first instance as an example, the first blue one. We will find its closest instance in another group, which means the red group. We will find its closest neighbor, and we will use the red features to modify the blue features accordingly. Not all of the features, only the features with Shapley values that are over a threshold. And we can see from the experimental results, even though we are trying to mitigate discriminant risk in these cases, we can still observe that the group fairness can be increased as well, and we are not sacrificing too much of the accuracy. And I should also mention that compared to all the pre-processing methods that we are using for comparison, the amount of modification of FairShap is the least compared to all of them. We can see through the last three and the last two columns here, the data fidelity is the optimal transport between the original data distribution and the adjusted data distribution. The training AR is the training adjusted rate. It means how many percentage of the data were modified in the training data. And FairShap doesn't need to modify the doesn't need to modify the test data. So this is clearly an advantage compared to CR and DIR. They are correlation remover and the disparate impact remover. And there is another observation that is the more modification, the more features that we are modifying in the original data set, and the better performance we will get using FairShap. And for FairShap, basically for summarize, we are trying to bridge explainability with fairness. And for the left side of the framework, we are trying to feature attribution using the Shapley value. And for the right side, we are trying to create new counterfactual explanation and train the model again on the counterfactual explanations and hopefully get fair models. By putting them together, we are getting generic fairness enhancing mechanism that could be integrated into existing machine learning pipelines, and it could also use different Shapley algorithms. So it's quite generic and transparent. To summarize, basically, I was trying to communicate with people that new fairness metrics are still needed, even though we already have so many in the literature, because facing the more complicated cases in the reality, new fairness metric can still be valuable to deal with multi-attribute and multi-valued cases. And we can also considering prioritizing individual fairness because it will offering strong and more flexible leverage compared with focusing only on group fairness. And we can also considering using explainability tools with fairness, and that would make bias mitigation more interpretable, target, and practical. And basically, in the following, I prepare some slides for they are some details relevant to my fairness metric, and I'm also happy to take questions.
Yeah, thanks a lot, Yijun. We have a bit of time if there is any questions, actually.
Yeah, if you like, I can also show you the algorithm, approximation algorithms first.
Sure.
Basically, yeah. And
Yeah.
basically, the figure 7 is trying to demonstrate that even though discriminant risk is different from counterfactual fairness, but somehow it could be viewed as a competitive measure as a counterfactual fairness, because if we use case study here, we're trying to we calculate a discriminant risk that discriminant risk of the models that is supposed to be counterfactual fear, and find that for those models, their discriminant risk is close to 0. So somehow we can say that the discriminant risk could be viewed as somehow a quantitative measure in these cases, even though it is different from counterfactual fitness. And I also would like to say more details about there is a difference between discriminant risk and the individual fairness. First of all, we don't need to specify any choice of similarity or distance metric here, and because by perturbing the sensitive attributes, we basically assume the preserved data are similar enough compared to the original data set, because only sensitive attributes are changed, right? And another difference is here is the instance pair for the individual fairness, they are all coming from the original data set. But in discriminant risk, the instance pair is not they are not all coming from the original data set. And there is also two difference in comparison with the group fairness measures. Firstly, we don't need to separate the original data set into two and calculate them separately. And also the group fairness measures, they are normally for one sensitive attribute, and usually they are bi-valued. I have mentioned that already at the beginning. And there are more difference if we can consider the counterfactual fairness. I use the causal fairness here, but basically I mean the counterfactual fairness and the proxy discrimination. The proxy discrimination is quite similar as the counterfactual fairness. I think the major difference between these two are the following changes on the proxy attributes. In proxy discrimination, they also don't consider the proxy the changes on proxy attributes as well. So in this sense, proxy discrimination is more similar to ours, the discrimination risk. Although proxy attributes also defined causal graphs. This is also quite different from ours. And even though the original counterfactual fairness, the form of the counterfactual fairness, it seems like they can work for more than one set of attributes only. But I find out if we need to really take that into account in practice, I somehow feel like we still need to pre-processing the more than one sensitive attributes into one super sensitive attributes. So I think they are basically still working on sensitive attributes, even though they could be multi-valued in these cases. And yeah, I already mentioned that the non-sensitive attributes, which is proxy attributes, may vary in counterfactual fairness, and The condition to achieve counterfactual fairness is much stronger because it requires um for all kind of cases the probability should remain the same. And the last one is DR can be proved bounded. This is another part that I didn't include in this talk. And I should also mention that they also share many similarities with existing fairness metric. First of all, it's following the principle of individual fairness, and it can calculate using the way of normal group fairness measure, just like the L prime here. You can calculate this way, although I didn't do so. And it can since it can be calculated over one data set, so we assume this means we can also observe from a statistical or demographic perspective, which would be similar to the group fairness. And as for the approximation of distance between set in the HFM, basically we only mention the approximation of a distance here. After we get a distance, we can just use the approximated distance distance directly and use the HFM equation to calculate and get the approximated fairness in those cases. So basic idea is for the more than one sensitive attributes, we will calculate the distance for one sensitive attribute on one by one, and then put them together to get a final maximal or average version of the distance here. And for one sensitive attributes, we actually have two versions of it. One is from the previous HFM, and the other is from the more generic cases. But I use the different colors to indicate their difference. So we can see that in the algorithm tool, we will use two. We can also use three. It depends on how many you would like to use. Normally, if you take more orthogonal vectors, in the calculation, the computational cost would be higher. And basically, we are just using orthogonal vectors several times and calculate them and get the minimal values among all of the approximated values. And as for the sub procedure, the acceleration of the distance here, they are quite they would look more similar. The idea here is we observe that the distance between similar data sets, they tend to be closer than others after projecting them onto a general one-dimensional linear subspace. So based on this observation, we will use a vector to project those data points into a one-dimensional linear subspace. So basically, this would be in Notion. We're projecting the original data set into one subspace. By using different vectors, we will get different subspace. Different vectors will correspond to different approximation. We will approximate several times and get the closest one as our final approximation. And we will run this sub procedure several times and get a closer approximation, because the approximation using the sub procedure would be they might be they may not be close enough, so we need to run it several times. So basically, that's the idea. I think that's basically all of it. This is just a summary about these two work because some people may be confused because I talk about too many distance here for different cases. So yeah.
I was a tiny bit confused by different distances. It's actually useful.
Well, let's just look at the table. I have two papers. They are all relevant to HFM, the
Mhm.
harmonic fairness of the manifold in this case. The first paper works for binary cases only. To be specific, one binary sensitive attributes only. So this is the second column, and the third column and the fourth column, they are coming from the second paper. They are trying to deal with one multi-valued sensitive attributes or more than one sensitive attributes only. So the third column is for one multi-valued sensitive attributes. And hold on. Sorry. The third column is the maximal version. The first column is the average version. The first row is the distance between set for the corresponding three scenarios, and the second column, the first column is for one sensitive attribute on one sensitive attributes only, where the first row, the second column is for one binary case, and the first row and the column 3 and column 4, they are for one bi-valued sensitive attribute sensitive attributes only. And the second column, it only the second column would be more than one sensitive attributes, because the paper one doesn't have anything relevant to this, so it's empty here. And the HFM, it's this is the name of the fairness metric, and they are calculated using the distance between sets, and we have three versions because the distance between sets, they have three versions in these cases. And in the following, the first to six rows, they are approximation algorithm, and the first row is for one attributes. They are either binary or multi-valued, and the second one is still for one sensitive attributes only. But since the first one is just a sub procedure, so the first row will run the fourth row several times and get a final approximation. And as for the last row, it would be more than one sensitive attributes only. It's only relevant to the second paper. I hope this would be more clear.
Yep, that makes sense.
Very complicated.
No, that yeah, I think it makes sense. Yeah.
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 Thank you. Yeah. The last page is just some literature. I just put some individual fairness in case anyone, because I realized I got some questions in the past that they asked how to calculate the COR index, so I just put them here. They are coming from the literature. They are not my work. Just for your information.
So I have a question about like earlier on in the talk when you were talking about fair shap.
Mm-hmm.
So I'm just trying to kind of understand the algorithm. So
Oh,
what happens? So okay, so I pair similar points together and then I'm looking for the feature that's like most influential and then I'm replacing that feature like influential in terms of like to this fairness metric, then I'm replacing that feature. Like so like could that like what happens when the feature that's most influential to the decision or the decision rule that the model's coming up with is like the demographic like group itself. So like say that the my best predictor um is predicting very different things for people in the two subgroups and it's specifically because of like their demographic feature being different. And so then like by training in this way, I then swap out the demographic feature of one to the other, but like I don't see how that would fix then when I like now you're saying like I in test at test time when I run this algorithm, I'm not doing this kind of pairing. I'm not modifying my features in any way. So I don't see how it would uh affect the down like positively impact the downstream fairness of the model at test time. Can you elaborate a bit?
um, I think the idea here is, first of all, we would like to um, mitigate the bias. Since we would like to mitigate the bias, we were thinking whether we can detect what kind of feature would be more important in the model when it makes biased prediction. So that's why we replace the original value function with DR. This is one of the fairness metric. And in this way, when we calculate the fairness values, uh, the values would represent uh, how much important these features would be uh, in the biased predictions.
But
So
oftentimes those features are either themselves directly indicative of like, for example, like a protected demographic group, or they are like strong proxies for those things, right? So how
uh,
does this work in that context?
mm,
Right, like zip code, for example, maybe one of my features is zip code, and that's the thing that is like has like the high Shapley value, but zip code is highly correlated with race.
mm, Uh, I assume in these cases, um, those um, those proxy attributes may get higher Shapley values. So they are more likely to be modified in the following because if the Shapley value of them are higher than a threshold, they will be modified in the following. And when we are modifying, we are trying to find their counterfactual. Um, uh, I was trying to say that we were trying to find the closest thing. Um, Basically, the idea is we're trying to find the closest instance that is the only changes would be sensitive attributes. That's why we try to use the nearest neighbor and use the neighbor's features to replace the instance features because we want those to be close enough so that how to say
But I guess I'm
um,
just like fundamentally confused as to how like modifying this and then training on it would lead to test time improvement for the unmodified data point.
Firstly, when we modify the data, there is nothing relevant to the machine learning models. The machine learning models are only involved before we modify the data and after we have done modifying. So the algorithm will be trained twice. Firstly, it will be trained on the original data set. Let's say this is model one. And after we modify the data set, we will use the same learning algorithm to train it on the adjusted data set and get model 2. And hopefully we expect the model 2 is higher it's fairer than model 1 and with similar accuracy in these cases. And meanwhile, we don't need to modify much. We don't need to modify many features in the procedure. Was that clear?
Okay, and just to be clear, then at test time, you're no longer modifying features, right?
No.
Okay.
That's why we specifically indicate that this is certainly an advantage compared to other removers, because they will need to modify the test data as well.
Okay.
Right. Is there any other question here? All right, Danny, there's no other question. Then thanks again, everyone, for coming. And yeah, I'll see you all next week.
Well, thank you.
See you guys. Bye.
Thank you. Thank you for the question and for listening.
Thank you.
Thank you.